Electromagnetic screen for removing Mars dust. Copolymerization of biodegradable polymer via polylactic acid with cysteine. Now, I don't know if I pronounced any of these words correctly, but these are just a couple of examples of student research papers presented at the Area Collegiate Chemistry meeting held in April. Students and professors from Mid-South colleges gathered at UT Martin to discuss research, academics, and the future of chemistry.
What you have here are students coming from a number of schools from sort of the Midwest here, from 7 or 8 states. And what we're doing here with this meeting is giving them an opportunity to take what they've done at school and in the laboratory and communicate it to their peers. It is a small version of a real technical meeting. And it gives them the opportunity to learn how to communicate their materials. Now, they're talking to their peers today, but some of the work that the student affiliates do outside of things like this, they do service work, they do projects, they take chemistry to the public, particularly the benefits of chemistry they take to the public, and talk to them about it.
One of the highlights of the day was a panel discussion about green chemistry, led by renowned chemist Berkeley Q and Paul Anastas.
Green chemistry is best defined as the utilization of a set of principles, there are actually 12 of them, that reduce or eliminate the generation and use of hazardous materials and the design of chemical manufacturing processes for chemical products.
Green chemistry means to both you and me the fact that we can look at the world a little bit differently. The fact is that all we have in this world is energy and matter or material. And because of that basic fact, and because chemists are the basic architects of matter and material, and because it's the material that we need to generate, to store, to transport our energy, that means that it can be designed by the molecular architects, the chemists, so that it's more environmentally benign to humans, and it can be done in a way that meets environmental and economic goals simultaneously.
Dr. Anastas coined the phrase green chemistry back in 1991 and led the development of the 12 principles which define the practice. He now advises the federal government on issues concerning science and chemistry. Both Drs. Anastas and Q say the practices of green chemistry are growing.
We don't see resistance. What we see is when people become aware, when people understand what green chemistry is, what the tools are, what the approaches are, this is something that is readily adopted. I've often said there's not a regulatory bone in green chemistry's body, and the reason is because people understand that through science and innovation, you can accomplish environmental goals without having to force people to do this. Industry is adopting this in large part because it's not only good for the environment, it's good for their bottom line.
We're seeing an increase in the number of universities which are embracing green chemistry programs every year. The program that's going to happen here today is a great example of students from all out the region coming to hear about green chemistry principles. I think there's a very active collaboration now between government, industry, and academics, which didn't exist several years ago in green chemistry and almost never exists. So that's a great outcome for green chemistry. If you measure the number of publications in the scientific literature that are appearing every year that cite green chemistry in the keyword index, the numbers are going up dramatically. Over 5,000 publications in 2002 and almost none in the early 90s. The number of patents that are being issued that have claim green chemistry-based processes and technologies is increasing. So I think everything is on the upswing. Having said that, I think we've reached the first plateau, and now we have to push a little bit harder to get to the next plateau.
So those of us in the general public, consumers, are there any examples of green chemistry that we can readily identify?
I think there are a lot of examples of products in the plastic industry, for example. There's a lot of processes that are being developed using biorenewable chemicals as opposed to petroleum-based chemicals to generate plastics which are useful in the product but then rapidly degrade when they enter the environment, which is a great win-win situation. I think there's a great example. Shaw Carpets in Atlanta, Georgia, has what they call a cradle-to-cradle carpet, tile, which if installed and then at the end of the life of the carpet tile, contact Shaw Carpets, they will come and they will remove the tile and then completely recycle all of the components. So that basically means they're not constantly introducing new feedstocks and depleting the environment of chemicals. Those are two examples.
The beauty of green chemistry is that because you are dealing at the molecular level, and the molecules don't know whether or not they're going to become a plastic or a paint or a agricultural chemical or a pharmaceutical, is that you can accomplish a wide range. All of those examples, new drugs that are beneficial and don't produce nearly the amount of waste in manufacture. New agricultural products that help food be produced far more efficiently and far greater levels without contaminating our water, our streams, our rivers. New plastics that will degrade harmlessly in the environment aren't made from depleting resources, limited resources, but yet have higher performance. Those are just some of the examples.
What about environmental impact? To what degree does green chemistry reduce pollution?
It's dramatic, because rather than taking the approach that we have had in the past of dealing with our problems after they are already created, in other words, cleaning up our past waste that goes into our water or our air, green chemistry is providing the fundamental tools to make sure that this pollution is never created, that hazardous substances are never used or generated. The difference between those two approaches is a tremendous difference, not only in resultant protection of the environment, but also meaning that you don't have to spend tremendous amounts of money in cleanup after the fact. It's really going back to the old adage of an ounce of prevention is worth a pound of cure.
There's an axiom called the Paracelsus Rule, which says the dose makes the poison. What that means is that any compound or any chemical at a certain dose can be poisonous. As you know, water can be toxic if you take in too much water. You can drown. Oxygen in a pure state is a very dangerous molecule because it's highly flammable. The manufacturing concepts of green chemistry tend not to adversely impact the quality of the drug that's produced. We have very rigorous analytical criteria that we have to meet. And so when we're applying green chemistry principles, we're constantly testing to determine that the methodology that we're using will produce the material in the right state of purity to minimize or eliminate side effects. You're right in saying all drugs do have side effects. Many of those side effects are very manageable, and many of those side effects appear at doses much higher than the dose that the patient takes.
Green chemistry is not only providing safer chemistry, it's providing more innovative chemistry, new materials, new processes that are working hand in hand to advance our quality of life and protect the environment.
Will we be able to notice the effects of green chemistry by what comes out of a smokestack or a water drain?
One of the basic tenets of green chemistry is that you only want to put into a process what is absolutely necessary to produce the product. So any type of waste, whether it's out of a smokestack, whether it's out of a waste pipe that usually goes out to a stream, all of those things would be affected because you are striving, in a perfect ideal situation, you are striving that anything that goes in to your process goes into product and not out to the environment.
So the amount of water coming out of a drain pipe may not be reduced, but if the company is practicing green chemistry, then the negative effects of that water can be reduced.
The moment that a chemist puts pencil to paper to design how a molecule is going to be made that's going to result in the paint, the plastics, the things we use every day, he is making decisions about whether or not this is going to be toxic or harmless, whether or not this is going to cost money to transport, whether you're going to need to have regulations in order to govern this. And through the proper design and the proper perspective, you can greatly reduce the cost and the environmental impact.